only to this type of problems. So what we're going to do a completely different category of problems in which we can use linear programming to solve it. And the problem category that I have in mind is what we call personnel scheduling problems. So you will see now a completely different family of problems. Personnel scheduling problems. So the best way, as I said, on this one I insist, I reiterate one more time, that there is no text. It's very similar to the previous one as far as the structure, objective function, constraints, variables, etc. But there is no specific numerical example from the handout or from a textbook to pass. So what I want you to do is to take notes. So let me give you beforehand, before we formulate and solve this problem, the application, so you can appreciate where these problems are coming from. The problem that I'm going to solve is applicable to operations which are 24/7, like for example the operations of a police department, a fire department, an ER room in a hospital. So it's one of those operations which are 24/7. And let me use an example from a police department, and I'll explain to you how does this problem arise and what we need to do to solve it. So first of all, let's assume that for a police department in a certain area, we try to get some estimate on how demand for services, how many police officers we need them to patrol in a certain area. How do we get the information, some preliminary information from the 911 calls? So what we do is we monitor the calls. That's how it is done in real life. So we monitor the frequency of calls, and based on the frequency of those calls, we have some preliminary estimates how many police officers we need in a certain area for a certain amount of time. Just to motivate the problem, in a real-life problem, demand for services may change every hour or every half an hour. But I want to put a time frame. So let's assume that based on what the data we get, that we have changes, the demand for services changes every 4 hours. So we monitor a specific area, and we say from 8 a.m. to 12 noon. So we're going to break down a 24-hour interval into 4-hour intervals. So we're going to break 24 hours into 4 hours. Every 4 hours, we say that demand for service changes. So now I'm going to write next to it at least. So based on the number of calls and so on, we can figure out what is the minimum number of people. At least we need 12 officers. What does it mean? At least 12 officers should be patrolling. We can have more.
12 times 4.
We can have more, but we cannot have fewer. So we can have either 12 or more officers patrolling that specific area. So then go from 12 noon to 4 p.m. As I said, I'm going to make up some numbers, but every 4 hours we have a change. 12 noon to 4 p.m. Let's assume the number goes up. We need at least 16. I mean, I'm making up those numbers, but the idea is that every 4 hours we have a change. So then the next time interval, 4 p.m. to 8 p.m. Let's say goes further up, 20. 8 p.m. to 12 midnight. Let's say it goes down. 12 midnight. 4 a.m. goes further down. Goes up. So I've just made up some numbers there. So what we have a snapshot of demand for police officers in a certain precinct, and here are the minimum numbers. So what is an acceptable solution is you can have more than this, but you cannot have less. So that's minimum requirements. Now, it's a simplification. I'm just letting you know in the real life problem that number changes hourly, sometimes depends on how big is the city, and so on. But here we use 4 hour intervals. Somebody's going to say, I don't see yet what are we trying to do here. What is the objective? Well, if we had the police force where each policeman works exactly 4 hours, there is no problem. Because if we have again, as I said, police officers which are required to work 4 consecutive hours and then they go home, there is no problem. You can hire 12 of them, then 16 of them, then 24, then 7. So there is no problem. The problem is because the shifts will be longer than this. So what are the requirements? The requirement is the following. Each police officer works 8 consecutive hours. We're going to factor in lunch breaks, etc. later. But let's start. The starting point is that we have each police officer who works 8 consecutive hours. So that means if somebody starts at 8 a.m., if we have a group of people starting at 8 a.m., how long are they going to work? Until 4 p.m. So they work, they can start, we can. So the question, let me finish all the data to get a holistic picture of what's going on here. So we have, let's assume you are the manager of this, the chief of this police department. So you have those requirements. You have to have at least that many officers every 4 hours on the streets on it. We take a snapshot of an individual day. And you have those requirements. And you have this restriction that each police officer too many. Each police officer works 8 consecutive hours. So you have those restrictions. So you are the chief of this unit, but you have those restrictions. That each officer works 8 consecutive hours. And what is your objective? Your objective is what is the minimum number of officers to staff this department. Okay, here is a restriction. Here is an objective. So this is the objective. Okay, so now you have the whole problem. That's the reason we call those problems personnel scheduling problems, because we have to assign employees to shifts. As I said, what is the application besides police departments? You see, this is a 24/7 operation. I took a snapshot of an individual day, 24 hours. But this, of course, I can generalize it to more days, etc. in a few minutes. But let's start, we need a starting point. So the starting point is what I have on the board. It's a 24-hour snapshot. We have change in demand every 4 hours. But we have a restriction. We cannot ask somebody, go, work 4 hours, go home, come back 4 hours later. The restriction is that we can assign the starting time, but the minute we have assigned a police officer a starting time, he or she has to work, what, 8 consecutive hours. So that's the restriction. So you may think, I can solve it by observation. It's not as easy as it looks to solve it by observation if I tell you what is the number. But what you're going to see is that this, believe it or not, this is another type of problem that can be solved using linear programming. And in this case, we're going to use a specialized version of linear programming called integer linear programming. Why? Up to now, even though all the variables were integer, remember when we were talking about number of units, etc. In this case, we have to pre-specify a restriction that we cannot have a solution where the solution is, because we're dealing with variables representing number of people, we cannot have fractional numbers. We have to have integers. So I'll show you how we can tell the computer beforehand to restrict the search only to integer values. So we're going to use a specialized version of linear programming called integer linear programming. So integer linear programming integer linear programming is a specialized version of linear programming in which up front we restrict the variables to be integer. So now, before I'll show you, it's very easy when we go to Excel to restrict the variables to be integer. But the main point here is, because this is a completely different version of the problem, how do we solve the problem? What are the options we have? The objective is clear: to minimize the number of employees working for this department, the number of police officers working for the department. The variables are police officers. But since we have flexibility, the only restriction we have is that if we assign somebody to come to work, let's say at 8 a.m., how long is that going to work? If he comes at 8 a.m., then work until what? 4 p.m. So that's the restriction, 8 consecutive hours. Well, somebody may say you can have people coming to work every 5 minutes. Obviously, this is redundant. You see, what are the key points? The key points here is when the demand for services changes. So what are the points at which we should call some people to come to work? What are the options? And then, of course, we're not going to tell. What I have to lay out here on the board is all the possible options. So when does it make sense to have some people come to work? It makes sense to have some people come to work at 8, 12, 4, 8, 12, only at the times when there is a shift in demand. That's an obvious simplification. It doesn't make sense to tell somebody come at 9 a.m. because demand changes at 8 a.m., 12 noon, 4 p.m., etc. So this is common sense that we should ask people to come to work and go home only when there is a change in demand. So in that case, let me define options, variables. So one option is, of course, at 8 a.m. I should ask some of my employees to come to work. So let me define my first variable, x1, number of employees, number of officers, working from 8 a.m. to 4 p.m. If they come at 8 a.m., there is a restriction. I cannot ask them to go home whenever I want. If they come at 8 a.m., I have the choice. I have the option to ask them to come at 8 a.m. But if they come at 8 a.m., how long they have to stay? Until 4 p.m. That's the restriction, 8 consecutive hours. So when is the next point in time I should invite some people to come to work? 12 noon. From 8 a.m., remember, we go forward, 8 a.m. The next point where there is a shift in demand is 12 noon. So let me define my next variable, x2, number of officers from 12 noon, 8 p.m. I define the starting point, and if I define the starting point, since the restriction is that they have to work 8 consecutive hours, obviously if they come at 12 noon, they're going to stay until 8 p.m. Next group, 4 p.m., 12 midnight. Next, 8 p.m., 4 a.m. At least I have to cover a 24-hour period. So obviously next one, yeah, midnight is another option. Starting at midnight, 8 a.m. Theoretically, there is one more option. Even though it looks like it's awkward, but technically there is one more option. What is the next option? 4 a.m. Because it's a rolling horizon, 24 hours. 4 a.m., 12 p.m. You know how it works in real life. It's seniority that dictates. The ones who are with the force the longest, they take the better ones. The ones who are just joining the force, they get what we call the graveyard. But then we're going to do an extension of the problem in which we're going to pay overtime. Not overtime. We're going to pay a premium for the bad shifts. So let me do this version first, and then I'll show you how we can have another version where we compensate for the bad shift. So we're going to have. So right now, what we do is we treat all the shifts the same. There is no cost factor. We assume. Look at what the objective here. The objective here is to minimize the number of officers. So what we are not factoring in, how much it's costing us to have somebody work in the morning or working in the evening. In the actual problems, when somebody works the unfavorable, let's call them shifts, usually we have to compensate them a little bit more. I'll do this version of the problem today, later today. So right now what I'm doing, I'm working on my options. So what am I said, I'm the manager of this department, and those are my options. So now you can see how I can put things together into a linear programming formulation. More precisely, integer linear programming formulation. So let's start with my objective. What is my objective? My objective is to minimize the workforce, the number of people working in this unit. So obviously, the objective function we don't know how many people work in each one of them. But what is my objective? To minimize the total. My objective is to minimize the total workforce. Look at what it says here. Minimum number of officers. So let me write over here the objective. So the objective is minimize. So we have a minimum function. Minimize 1 plus 2 plus 3
plus 4
plus 4
5
plus 5
and
plus
6.
6. So that's the objective. Sum, yeah, I'll use the sum. I'll use the sum. Actually, I mean, if you want mathematically, this can be, the shortcut is sum xi, I equal 1 to 6. If you want to short it, this is a shortcut. Sum starts, sigma stands for sum.
Sigma para sumar.
I goes from what? 1 to 3 up to 6. That's a shortcut.
Factorials, factorials, right?
No, factorial is, don't confuse it, it's product. X1
This
times
is
X2.
sum.
This is sum.
This is
X1
sum.
plus X2. So what is
Sigma.
here is
Sigma.
just, I mean, you don't have to do that, but since somebody asked me, I is like a subscript. I subscript. And here it says it goes from 1 to 6. So if you want to write this analytically, to expand it, it's going to give you this. You see what it says? Start adding xi from 1. So the very first one is x1. What is the last one? The last
6.
one is up there, 6. So if you expand it, how it's going to read? It's going to read like this. So that's it. This is this. You don't have to do it, but because somebody asked me if we can use the shortcut. So the shortcut is the sum. You put I as a subscript, and you below the sigma, you say where it starts. Above the sigma, you designate where it ends. So it starts at 1, it ends at 6. Okay, so let's go to restrictions. So what I want to do, let me flip those. So what I want to do, I want your help. So I'm asking you a question. During that time interval, I have 6 groups. Those are the 6 groups there, 1, 2, 3, 4, 5, 6. From 8 a.m. to 12 noon, which one, if any of those groups are working? Who is working between 8 a.m. to 12 noon?
12 officers?
No, not how many. Which groups? 1, 2, 3. I have 6 groups. X1, X1 is working. Let's see. X1 is working from 8 a.m. to 4 p.m. So you're right. X1 is working. Is anybody else working between 8 a.m. and 12 noon? That's the question.
X2.
6. This group. Let's see. 6, 4 a.m. to 12 noon.
And X2?
No,
No?
X2 is not because they start at 12 noon. So forget, 12 noon is the cutoff point.
Yeah.
So they are not working. So during this interval, who is working? 1 and 6. Okay, so what is the restriction? At least 12 people should be working between 8 a.m. and noon. So I know, just by doing what I just asked you minutes ago, we know who is working, 1 and 6. So we don't know how many people belong to 1, how many people belong to 6, but combined 1 and 6 must be at least what? 12. So that's how we work on these problems. So we say the restriction is that 1 plus 6 must be greater or equal than 12, and I put a check mark here. I took care of this restriction. You see how it works? So I go through time interval one by one. I ask you the question, who is working? And the combined number of people working during that interval must be at least, let's take the next one, noon to 4 p.m. So let me ask you the same question for the next one. So let's go.
What is this that we're looking for? The constraints, basically?
The constraints, yes, because look at what it says, at least 12 people. So I say, I don't know what is the breakdown between 1, 2, 3, 4, 5, 6. But 1 and 6 together, because both of them are working between 8 a.m. and noon, together, combined, must be at least 12. So I'm asking the same question here. So let me circle this one. Between 12 noon and 4 p.m., I need at least 16 officers. So who is working? Which group is working between 12 noon and 4 p.m.? Who is working? X2 is working. Who else? X1. Look at X1. 8 a.m. to 4 p.m. So it's 1 and 2. So if you check the next interval, 1 and 2 are working. So the two of them combined must be at least what? 16. So 1 and 2, 16. You see how it works now? So what we do, we check its time interval, we locate the groups who are working during that time interval, and we say the combined number must be at least whatever is given. That's how it works. Alright, let's do the next one.
En mi vida me habían hecho tantas preguntas.
It's x2 plus x3.
There is a pattern. Now some of you may see every 4 hours what happens. Somebody goes home and the next group joins the force. It's a pattern. So the next one is 2 and 3. But spend the time, don't take my word for it. Spend the time and ask the question. So the question is always, for example, right now I'm down here. I have done the first two, I'm down here. I'm asking who is working between 4 p.m. and 8 p.m. I'm always asking the question, who is working during that interval? So it's 2 and 3. So 2 and 3, at least 20. Check mark. So next.
Is it less or greater than
Greater than. Did I put less? Because look at what it says there. It says at least. You see the key phrase? At least. So when the statement is at least, we must have at least that many numbers.
At least or more.
At least means either this number or more, not the other way around. If it was the other way, I would say no more than. But if it says no more than, you know what's the solution? Zero. You're not going to assign anybody. That's the reason you have to have a minimum. Think about it. If somebody said, I need no more than 12, that means you're okay with nobody. Then the solution will disintegrate into zeros. So that's the reason there we need to say at least that many people. We need a minimum number of people working. Okay, next one. 8 p.m. to midnight. Which groups are working? 8 p.m. to midnight.
x3 and x4?
3 and 4.
So it's going to be, so basically, I see how it goes. Next one should be x5 and x4, x5 and x6, right? x5, x4 and x5.
The next one, now you see the pattern.
X4 and X5.
But again, don't take my word for it. I welcome you when you work on a problem at home to check these things. It's always, yes, there is a pattern. One group drops and the next one joins. That's how it works. But I don't want you to take my word for it. I want you to check. So right now we're in between midnight and 4 a.m. So it's 4 and 5. So 4 and 5 greater than 6. And the last one is the 4 a.m. 5 and 6.
5 and 6 greater than 10.
10. Okay, now other constraints. X, since now you are familiar, I introduced the shortcuts using a subscript xi greater or equal than 0. I goes from 1 to 6. That means each one of those groups must be at least 0. So we put this constraint. And I'm going to put another constraint, xi equals integer. This is new. So we're going to say, in this case, we want each one of those values, x1, 2, 3, 4, 5, 6, to be restricted to be an integer number. Why? Because they represent humans. So up to now, we didn't explicitly impose it, but this is an opportunity for you to see how it works. So here we have the following problem. Minimize the sum of x's, 1, 2, 3, 4, 5, 6, subject to those constraints. Each xi is greater or equal than 0. That means 1, 2, x1, 2, 3, 4, 5, 6. x1, 2, 3, 4, 5, 6 is integer. So this is what we call a personnel scheduling problem. What I did here is a simplification. I took a snapshot of a 24-hour interval. Let me solve it using Excel. Again, I'm not going to ask you to solve, but here I'm going to solve it because I want you to see the benefits of knowing the solution. So let me solve the problem using Excel, and then after I solve it, and I show you the what-if questions, how we can utilize the solution to make business decisions. I'll show you two generalizations, which I'm not going to ask you to do it. One I'm going to ask you to do it is to compare this from a minimum manpower problem to a minimum payroll problem. Right now we're trying to minimize manpower. But in real life, usually, if you have differentiated wages, that means you pay more at night versus daytime, the objective is not to minimize the number of people. The objective is to minimize the payroll cost. So we'll do one generalization where we minimize payroll cost, that I'm going to do. And then there are two generalizations to make it more realistic, to solve the problem on a weekly basis. Because right now, what did I do? I took a snapshot, 24 hours. Is that Monday? Is it Tuesday? So for real life data, what do you have? You have this. You have this for Monday. You have another one for Tuesday, one for Wednesday. So it goes on a, if it's a 24/7 operation, It's not only 24 hours, take a snapshot of 24 hours. Of what day? So you take a snapshot of Monday, then Tuesday, Wednesday, Thursday. That I'm not going to do the math. I'm going to show you how it is done. I'm not going to do it. But the payroll minimization is simple. The generalization is simple. I'm going to do it here with you. But first, let's solve this problem.
What's the name of this problem?
Personnel scheduling problem. Let's minimize personnel for a 24/7 operation. I mean, where it originated from? It originated from the NYPD. The NYPD has this data, and the demand for services not only changes by day, it changes by the hour. And they wanted to, and they have some electricity. So they wanted to solve this problem, and they called experts who use these techniques. These techniques are called operations research techniques. So this, but the generic name for this problem is personnel scheduling problem.
So would this have to do with FTEs, and you're trying to minimize FTEs, or people working?
The two objectives: to minimize the number of people working in the hospital, and that's this version. It's a simplification. This version is to minimize the number of people. But in a few minutes, I'll give you a version. If you pay differentiated wages, you pay more for the night shift. I'll give you a version where you minimize the payroll cost of running this 3 hours. So in a hospital, it applies to a 24/7 hospital. Is a good example. Even though the origin of this problem is a police department, obviously the direct application besides police department is what? The fire department and an ER room. Those two I can think of. I cannot think of anything else right now. But at least the police, besides the police department, we can utilize this for a fire department and in a hospital, ER. But the name of the problem is personnel scheduling. It's a personnel scheduling problem. Okay, again, you're not responsible for the solution. I've said it many times. But let me go through and solve it to see how we can utilize the solution. Because when we solve the problem, let me ask you something. When I solve this problem, remember those constraints, this is in column B, we have numbers. Here in column A, numbers will pop up. Can somebody tell me the numbers will pop up here? Let's take this one. What number will pop up here? Can a 10 pop up here?
7 or no?
Yeah.
No. Look what it says. 1 plus 6 greater or equal to 12.
Okay.
So, what is ideal for us? A 12. But now we may have numbers which are bigger than 12. Here you can have a number which will be 12 or higher. What number will pop up here? 16 or higher. What number will pop up here? 20 or higher. Just to give you heads up. If all the numbers that pop up here are equal to this, perfect. We don't have redundancy. If some numbers here are bigger than this one, what happens? Redundancy. So we have some people that we don't need. Why is this happening? Why do we have redundancy? Why can't we tell these people go home? Because of the restriction, 8 consecutive hours. You may need this person only for 2 hours. But his or her contract says 8 consecutive hours. You cannot say, I need you from 8 to 10, go home, come back at 11. It doesn't work this way. So that's the reason we need a computer to solve this problem. Because there will be some redundancies, unless, because I made up these numbers, unless I came up with some set of numbers where everything clicks, there will be some redundancy. Why is it important for us to know the redundancy? Because if this is not an isolated unit, let's assume it's a police precinct, and there's another one next door. If you know, you need to know when is the redundancy. If you know when the redundancy is, you tell these people, yeah, I have to pay you, but instead of patrolling 8th Street, go and patrol 20th Street, something like that. You see, why is it important for you to know how much and where is the redundancy? Because then you can reallocate these officers to a neighboring principal. So this way, you have to pay them, but you don't have to tell them, sit idle doing nothing. You say, go and patrol next door. Okay, let's solve this problem first to see my, oh, sorry, forgot.
So, you're telling us that we don't have to really necessarily be responsible for solving this problem.
You're responsible to do this, you're responsible to do this. Then I'll tell you, assume that by using solver, we solve this problem, the solution is x120, x250. But I need to get those numbers from the Excel. When I get those numbers, I'll ask you, how much redundancy do we have? So the reason I'm solving here is because I have to figure out, if I solve this problem and I get the best possible solution, how much redundancy do I have? That's the reason I'm solving, because if I don't solve it, I cannot, as I said, it's not as easy as you think to start guessing numbers here. It's not as easy. There are so many combinations, that's the reason we let the computer do them. It's not as easy. Okay, so now let me, again, open a new spreadsheet. Okay, first step is variables. How many cells do I need for variables? How many variables do I have now? 6. So I'm going to reserve A1, 2, 3, 4, 5, 6 to write x1, x2, x3, etc. So 6 variables right now. So initially, let me put zeros there. Okay, let's write the objective function over here. Equal. Now, the objective function here has a specific structure. A1 plus A2, so is there a shortcut I can do? Sum. I can put equal sum A1, A6. I don't have to type A1 plus A2 plus A3 plus A4 plus A5 plus A6. There is a shortcut. Equal sum. Highlight. Okay, you don't have to do it. You can write equal A1 plus A2, etc. But this is a shortcut. So I just wrote there equal sum A1 up to A6. Obviously, at this stage, if I click enter, what is the solution? 0. Solution is 0. Okay, constraints. So let me write them starting here. Okay, look at what I'm going to do. The first one, left, again, look at those 6 constraints. Very similar structure. The left is equal A1 plus A6, A1 plus A2, greater or equal number. So on the left, let me start with this one, equal A1 plus A6. Then the next one, equal A1 plus A2, A2 plus A3, etc.
What did you put in the D1?
Equal sum A1, and I highlighted A1 through A6. Why? You need to know why. Look at here. Why? This is the objective. You see the objective up here? That's the reason. So that's what I wrote. Okay? Instead of writing one by one, A1 plus A2 plus A3 plus A, I just put sum there. Equal sum A1 through A6.
And zeros from 1 to 7, from 1 to 6, that's considered our constraint, right?
No, 1 to 6, A1 to A6 is the space where I'm going to write the variables. I'm going to write the answer. So that's the reason I put zeros. Okay, so now equal. My first constraint is A1 plus A6. The left. A1 plus A6. Look at how I write it here. Equal A1 plus A6. What is my next one? Equal A1 plus A2. Then A2 plus A3. A3 plus A4, etc. So I'm going to write them down here. Equal A1 plus A6. Next one. Equal A1 plus A2. Next. Equal A2 plus A3. Next. Equal A3 plus A4. Next. Equal A4 plus A5. Next, equal A5 plus A6. Okay, what I did, I wrote all of those things. One equal A1 plus A6, A1 plus A2, A2 plus A3. Now I have to type the numbers, 12, 16, 20,
4, 5.
12,
1 and 6.
16,
Then 1 and 2.
20,
10,
1 and 6.
10, 6,
You're doing
and
it
10.
The first one is 1 and 6. I already did it. The second one, 1 and 2.
So I'm ready, I'm good to go now. So what I'm going to do is something new here. When I click the solver and so on, something new. I have to tell the solver that I'm restricting all of those variables, A1, 2, 3, 4, 5, 6, to be integer. That's new. It's very simple, but it's new. That's the reason I'm going to show you how to do it. All right, let's go through the steps now. Solver first. So the objective, set objective, the objective is D1. And what are we doing? Minimizing. Okay, be careful, click minimize. Remember, when you open it up, it goes to max. So we have to switch to min. So the objective here is to minimize. So we have D1. In D1, I wrote sum 1, 2, 3, 4, 5, 6. That's my objective. Minimize D1. Change in cells. Let me click change in cells. Which one are my change in cells? 1 through 6. A1 through A6.
That's easy.
A1 through A6. Now click Add Constraints. A, 8, 10, 11 to 13. Be careful. Greater or equal. So I have to shift here. Greater or equal. B, 8 to 13.
Okay.
So I'm entering this A8 to 13, greater or equal B8 to 13. I'm going to click Add. So all of those constraints are these. So this greater or equal than this. So I have the bulk of the constraints there. But I have to click Add because I'm not done with it.
Now you have to do the 0 one.
Yeah, now I'm doing, let me do the 0 one. A1 through 6, greater or equal, greater or equal again, 0. Add again, because now what is missing? That they are integer. So something new. How do I tell Excel that the variables are supposed to be integer? So something new. I'm going to highlight them. A1 through A6. So first let me highlight them. A1 through A6. Okay, look at now in the middle. One of the choices, I clicked the middle field. Look at one of the choices, INT. You see that choice, INT? Select it. Yeah, it's a shortcut for integer. It populated the word integer. I didn't do anything. I just selected INT. And I click OK. So it's easy in Excel. You just select, you highlight the variables, and where it said less or equal, greater or equal, one of the choices was INT. By selecting INT, the word integer populated the right field. I didn't do it. The computer did it automatically. So now look at the problem description. Minimize D1. D1 is the sum of A1 through A6. Change A1 through A6. A1 through A6 are integers, are greater or equal than 0, and A8 to 13 is greater or equal B8 to 13. All of these, A8 to 13, greater or equal B8 to 13 is this. So if I click solve now, what's going to happen? The answers will be, values will show up in A1, 2, 3, 4, 5, 6. Those numbers will be the best selection of how many people to work A1. What is A1? A1, it's up there, 8 a.m. to 4 p.m. A2, 12 noon to 8 p.m. So I'm going to get the best selection, so the total number of employees is minimal, and I satisfy the demand. I have at least 12 working in the morning, 16 working in the afternoon, and so on.
The solving method will be the same, GRD nonlinear?
Yeah, I'm not making any changes.
Okay.
Yeah, it's because this is for very sophisticated problems, but for those simple problems, the solving method is, let me try first of all to see.
All the constraints are binding.
I think this is.
Really?
Yeah, it's all done.
Well, that's true because they all equal each other.
No, unless I'm dyslexic.
No, there's one.
There's one.
There's one. There's one. It looked like it.
One.
Oh, 12 and 10.
Oh, I was looking at the bottom.
No, at least one.
I was looking at the
Because I tell you, I've been doing this for years, unless it's very hard for me to guess numbers. I guess those numbers, the 12, 16, and be perfect. Yes.
I'm sorry, I missed it. Why did you click the option for integers again?
Okay, I highlighted A1 through A6, and where it said less or equal, greater or equal, one of the choices there was INT. I selected INT, and it put the word integer on the right automatically. I didn't type it, I just selected INT.
And then you click add.
Yeah, add. Okay, finally, because that was the last one. Click add, and then you say okay. That's all we have. Okay, let me tell you two comments before I'll answer the questions. But two comments. In this case, it's possible that you have a different solution, different values for A1, 2, 3, 4, 6, as long as the value in B1 is 38. So it's a possibility here that you have more than one choice of getting the best solution. That means as long as the total number of officers is 38, you may get there through a different allocation of people. Did it happen to any of you, or all of you got identical numbers with me, 5, 11, etc.? Everybody got the same. Okay, so what we need to do now is let's interpret the solution. Let's interpret the solution. The solution can be interpreted as follows. If you want the minimum possible manpower for this department, the answer is 38. So that's the direct solution. What is the minimum number of employees? that you can hire and allocate to 8-hour consecutive shifts so that you have the minimums. What are the minimums? 12, 16, 20 there. So the answer is 38. If you try to do it by hand, that's what I'm saying, you're not going to get there. It's much harder to get. It's impossible, I'm telling you. Unless we have somebody here with IQ 240 and they can see things, it's impossible to do it by trial and error. It's impossible to do by trial and error. So that's the quick solution, the quick answer. But now how can we utilize this answer to minimize surplus? So first of all here, let me give you another value. Slack. So what is the definition? Somebody's going to say, let's define the slack. Remember, slack represents, in general, slack represents redundancy. So slack is a generic term representing redundancy. So let me give you some additional information for personnel scheduling problems. How do we define slack? Let me give you a definition from the airline industry and then I'll come back to this problem. So let's take an example from the airline industry, and we try to find out which airline has a higher volume of work. An airline that flies, let's say, 10 passengers from Miami to Fort Lauderdale, or an airline that flies 1 passenger from Miami to China. So you see here, why am I asking this question? So how do you determine the load factor of an airline? Simply by the number of passengers flown? No. It's the number of passengers times how far they flew. So why am I saying that? How do you define slack? Simply by the number of officers which are idle, not needed? No. It's number of officers times for how long. So you may have a solution where you say, I have one guy who is not needed, but this guy may not be needed only for 5 minutes. And in another solution, you may have the other way around. You may have 10 guys not needed, but for 5 minutes each, or you may have one guy for 2 hours. So which one is better? So what I'm trying to say, 1 unit of slack here cannot be just number of people. It has to be number of people times for how long. So let's define 1 unit of slack. 1 employee being idle for 1 hour. So again, the point I'm making here, when you try to evaluate 2 different solutions, which one has more slack versus less slack, you cannot use 1 dimension, number of employees. You have to use 2 dimensions. It's not only how many people are not needed, but it's also important to know for how long. So 1 unit of slack here is 1 person who is idle for 1 hour. I just define 1 hour. Somebody say for 4 hours. It's your choice, but you have to have a definition of 1 unit of slack which takes into account what? Time. You cannot have slack defined only by how many people are redundant. You need to know how many for how long. So I can define 1 employee for 1 hour constitutes 1 unit of slack. So now the question in this solution is how many units of slack do we have? So the question is, let me use this one. How many units of slack do we have? First of all, if you look at the first constraint, binding. Remember what I said? When the left is equal to the right, those numbers are equal, no slack. Binding, binding, binding. Number 4 is not. Let's keep it. 5 and 6 are binding. By the way, as you can tell, this is a very good solution. Almost everything is to the limit.
Why?
So the only why is because, as I said, equal numbers. When the 2 numbers are equal, the constraint is binding. There is no redundancy. Slack implies redundancy. Only slack is this one, number 4. So let me highlight the one that has slack. This is the one. This is the only one where we have some slack. So on the left, the value is 12. Remember, those constraints are greater or equal. So on the left, the value is 12. On the right, the value is 10. So how much slack do we have? The quick answer is 2. But look at how I define slack. 1 unit of slack, so let me say 1 unit of slack is equal 1 employee being idle for 1 hour. So in that case, how many units of slack do we have? The correct answer is 8. Why?
4 hours on shift.
Exactly. That interval is 4 hours long. So 4 hours long, okay? It's this interval here, this one. So it's 4 hours long. And during that 4 hour long interval, we have 2 extra employees. So 2 extra employees times 4 hours each. So the answer is this constraint generates 2 times of 4 equals 8 units of slack.
The opening that says that we have 2 employees
that are idle for a 4 hour interval. And as I said, what is the practical use of it? The practical use of it is if there is a neighboring department in a hospital, because most of you have experience, let's assume there is another department next door. So let's assume those 2 are nurses. You can say for those 4 hours, of course, by contract, I cannot send you home, you have to be here, but go next door. Something like that. And police departments do it all the time. Because there are neighboring precincts. So they say, go patrol next door. Instead of patrolling here, go patrol in the next precinct. That's where you need. So this is important. I always emphasize this part, that this is important to know when is the redundancy and where, because what is the reason for knowing that? You reallocate. If you know where is the slack, you can always reallocate.
So because there's 8 units, it's 8 hours of idle time, right?
There are 2 extra people during that time. But how long is this interval? Look at this interval. This interval is this one, 1, 2, 3. This, how long is that? 4 hours. So there are 2 people, 8 units of slack. 2 people, and each one of them is sitting idle for how long? 4 hours each. 2 people, 2 persons, each person is idle for 4 hours. So 2 persons times 4, 8 units of slack. What is 1 unit of slack? 1 unit of slack is 1 person for 1 hour. We have 2 persons for 4 hours each. 2 persons for 4 hours each, 2 times 4, 8. Okay, what I'm going to do is I'm going to assign now the generalization of this as a homework problem for next week. So what is the generalization of this? As I said, let me draw a line. So assume that the hourly wage
This is a new one, right?
It's an extension of the previous one. It's an extension. So remember I told you the basic problem we just solved, the objective was to minimize manpower. So now I'm making a generalization where you'll see the objective will be to minimize daily payroll costs. So additional information, the hourly wage $10 per hour for each hour work between 8 a.m. and 12 midnight. And 15 per hour Okay, now we have differentiated wages. We pay $10 per hour per person for each hour that they work between 8 a.m. and 12 midnight. And we pay 50% more, $15 per hour, for each hour work between midnight and 8 a.m. So everything else stays the same. So what is the question now? The question is reformulate with the objective of minimizing daily payroll cost. Okay, I want you to work on that as an exercise, and I'll do it in class next. We have class a week from today, so I'll do it in class myself. But I want you to try. I can give you the hints. What's going to change? What's going to stay the same? There will be only one change. The constraints will stay the same. Nothing changes. This is going to change. The objective function will no longer be to minimize the number of employees. The constraint here will change. will be to minimize how much it's costing us to have those people. So the definition of variables the same. Variables will stay the same. Constraints will stay the same. The objective function will change. So I'll do it first thing next week. So again, one more time. What is going to stay the same? What is going to change? The definition of the variables will remain the same. No change in the variables. Exactly the same variables. The constraints, all of the constraints, including the variables being integer, the variables being greater or equal than 0, and all of this will remain the same. Only the objective function will change.
So you will, for example, let's say.
You have to figure out. Let me give you a hint. For each one of the groups, 1, 2, 3, 4, 5, 6, you have to figure out how much money each one of them makes, and then the objective function will be how much money each individual makes in this group times x1 plus how much money x2, etc. So it's
Times.
not that hard, but I want you to have an opportunity to take a look at it.
Can you repeat that?
Yes. So what I said is there will be only one change in the objective function. In the objective function, instead of having each group times 1, we have each group here times how much money they make. So for this person, if there is one person working in this shift, how much money he makes. Plus, how much money this person makes times x2, etc. Again, I want you to try. If I do it right now, you're not going to learn. So I want you to try. Okay, let's have a short 5 minutes break if you want to look at it, and then we'll continue.
Okay.